Hey guys, welcome back to the channel. If it's your first time here, my name is Aiden Potts and we go through math and physics tutorials as well as how to improve the mindset and learning skills of a student. In this video, we're going to be verifying trigonometric identities. We're going to be using our compound angle formula, which was done in part 1. We're going to be using our double angle formula, which was done in part 2, as well as some other special patterns to ensure we can make the left side equal the right side. By the end of this video, you'll understand the strategy and the steps that need to be taken in order to solve these trigonometric identities. If you guys find this content helpful, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. So today, like I said, we're going to be proving, solving, and verifying trigonometric identities. Whenever it says either proving, solving, or verifying, it really means the same thing. To solve these identities, we're going to be using our compound angle derivation or compound angle formulas, which was done in part 1. We'll be using our double angle formulas, which was done in part 2. We'll also be using our Pythagorean theorem identity, and also we're going to have some patterns that we're going to have to watch out for. So here we have perfect square trinomials, so either the positive or the negative version. So this is where you see a plus b squared in brackets, and that equals a squared plus 2ab plus b squared, as well as PST negative, which is a minus b squared, which equals a squared minus 2ab plus b squared. Finally, we'll also be wary of noting for difference of squares, which is a squared minus b squared equals a plus b times a minus b. Okay, so here we have our first example problem. And whenever you see a trigonometric identity and it'll say prove this identity or verify this identity, the first thing you should always do is write out the cotangents or tangents in terms of sine. So 2 times cos x over sine x, and then over 1 plus cos squared x over sine squared x. So now once you've written out the equation in terms of sines and cos for the tangent or the cotangent, what we're going to do now is work with one side of the equation. And this is very important for identities. You don't want to be going across the equal sign, so left and right side. You want to work with either the left side or the right side first. So in this case, we're always going to work with the side that looks a bit more complicated, like sometimes like the meteor side, or like the thing that we think we can do more transformations on or more identities on. So that's the left side here. So my first step here is I'm going to multiply the numerator and the denominator by sine squared of x. This will cancel out this denominator here and make it a little bit easier to deal with. And the reason I can write sine squared x over sine squared x and multiply it is because this is really just saying 1 over 1. So I'm multiplying it by a fraction that's equivalent to 1 over 1. So effectively I'm not actually changing the identity or changing the equation here. So when I do that, I'm going to multiply this sine squared x, and in the numerator will be cos of x, and then this squared is going to cancel out with that one, but there's still a remaining sine x here. And in the denominator we'll get, well, 1 times sine squared x, that's sine squared x, and then it'll be plus, and this will be cos squared x. Now this is where the Pythagorean theorem identity comes in. So wherever you see sine squared x plus cos squared x, we know that's equal to 1. So in the denominator we can write 2 cos x sine x over 1. And that is equal to sine of 2x. We also know that our double angle formula for sine of x, like we have sine of 2x, is really just equal to 2 sine x cos x. And that's exactly what we have here, just in different orders. So I'm going to write 2 sine x cos x equals sine 2x, and then I can write this is equivalent to sine of 2x, which equals sine of 2x. And now the left side of the equation is equal to the right side. So moving on to example problem number 2. On the left side, it looks to be more transformations or more identities can be used in this situation, and the right side I'm just gonna leave for now. The left side here we have this cos 2x, so that's a double angle identity. I'm gonna write the cos of 2x is also cos squared x minus sine squared x. And again, it's super important that we understand the derivations of these because that's what's gonna enable us to see these relationships when we start the problem. So now in the denominator, well, cos x plus sine x squared, that's the same as writing cos x times, cos x plus sine x multiplied by cos x plus sine x. It's just the same thing twice, right? And now this is kind of where I think, people don't really see it, but again, it comes with experience, and I think the more you do these problems, the better you'll get at them. But we have to note that this is actually a difference of squares pattern. So this difference of squares will equal a plus b multiplied by a minus b. So this numerator can be written as cos of x minus sine of x multiplied by cos of x plus sine of x. And the denominator will have cos of x plus sine of x multiplied by cos of x plus sine of x. Now here we can see that this will cancel with this because it's the numerator is the exact same as the denominator. And now we'll have cos of x minus sine of x over cos of x plus sine of x equals the other side, which is cos of x minus sine of x, and finally cos of x plus sine of x. So we could say that the left side is equal to the right side. So for example problem 3, we have what looks like two compound angle identities. So we have both addition formulas for cos. So I'm just going to rewrite these in terms, and I'm going to deal with the left side and I'm going to deal with the right side a little later. So it's going to be cos of pi over 4 times cos of x minus, so this is all still in here, minus sine of pi over 4 sine of x. And then now we'll move on to this part of the equation. It's going to be a very similar thing, so it's the same addition formula. So plus, and this is going to be cos of 3 pi over 4 times cos of x. And then now it's again minus sine of 3 pi over 4 sine of x. And now we know that pi over 4, or 45 degrees, if we're working in degrees, is part of our special angle triangle. So I can rewrite cos of pi over 4. I know that's just 1 over root 2. So I can do 1 over root 2 times cos of x, and then minus, and then sine of that angle is the same thing. It's 1 over root 2 sine of x. Now plus, when this here, we have cos of 3 pi over 4. That's the equivalent of cos of pi over 4 coming from the negative x-axis. So that means we're in quadrant 2, and based on cast, if we go through this acronym here, cos is negative in this quadrant, and that's where this angle 3 pi over 4 will exist. So what we need to do is cos of 3 pi over 4 is going to equal negative 1 over root 2 multiplied by cos of x, because that negative 1 is in the negative x direction, and that corresponds to cos. Then minus sine of 3 pi over 4, well, that's the vertical direction, and in quadrant 2 sine is positive, so that's just going to be minus 1 over root 2 sine of x. And at this point, this 1 over root 2 cos of x will cancel with this negative 1 over root 2 cos of x, because we're adding them. And then now we'll have negative 2 over root 2 sine of x. And typically, teachers in textbooks, they're not going to want this radical in the denominator. What they want to do is rationalize the number. And the way we do that is we multiply the number by the, radical in the denominator. So it'll be the numerator root 2 over root 2. So multiplied by what we have here. And again, I can do this because root 2 over root 2 is really just equivalent to 1, so I'm not changing the formula here. This is going to be negative 2 over root 2, and then over, well, root 2 times root 2 is actually just 2. And that'll be sine of x. And finally, we're going to cancel out this 2 and 2. So we get negative root 2 sine of x equals negative root 2 sine of x. And again, this left side equals the right side. Okay, so moving on to problem number 4. So again, the first thing I'm always going to do is, if I have a reciprocal function or I have tans and cotangents, what I'm going to do is always just write them in terms of sine and cos. So before we do anything, I'm just going to rewrite this in terms of sines and cos. Okay, because secant is 1 over cos, and cosecant is 1 over sine. Tangent is sine over cos. Cotangent is cos over sine. And now I'm going to work with kind of the left side and the right side in this problem, but I'm first going to start with the left side. So sine of x plus cos of x multiplied, and then I'm going to get a common denominator. So when we're adding fractions, we always need a common denominator. So I'm going to do a big bracket here, and I'm going to say that the common denominator will be sine of x multiplied by cos of x, right? Because we're just multiplying these two denominators. Obviously, that'll be common to both of them. And then now I have to look, okay, well, to get from cos of x to sine of x cos of x, I'm going to have to multiply the numerator as well by sine of x. So this will be sine squared of x. And then we're adding, and then the same thing over here. To get sine of x to be sine x cos x, I'm going to have to multiply the denominator by cos of x. So I have to do the same thing to the numerator. So we'll get sine of x squared plus cos of x squared over sine x cos x. And then from our Pythagorean theorem identity, sine x squared plus cos x squared is really just 1. So I'm going to write this sine of x plus cos of x over sine x cos x. And then now I'm going to bring in what we had on the right side. So we had 1 over cos of x plus 1 over sine of x. And I'm going to do a similar thing on this right side here that I did for this fraction. I'm going to get a common denominator. So this will be sine of x cos of x. And then to get from cos of x to sine x cos x, I multiplied by sine of x, so the numerator will be as well. And similarly, we're going to have this 1 turn into a cos of x. So now that I kind of did everything I could on the left side, I manipulated the right side just to write it a little bit differently. And then now I think it's clear to show that sine x plus cos x over sine x cos x is on both sides of the equation, so the left side equals the right side. And that's what we have right here. Okay, now looking at example problem number 5. Here it looks like we have a subtraction formula, so a compound angle formula for cos, and another compound angle formula for cos, but the addition formula. So I'm going to work with the right side here, and I'm going to say that we have cos of x minus y, so that's going to be cos of x, cos of y, plus sine of x, sine of y, and then minus, I'm always going to put brackets whenever I see a minus, to ensure that I can factor in that negative in the future and not forget about it. So with this addition formula, it'll be cos x, cos y, and then it'll be minus sine x. Now if I distribute that negative, so I'm just going to rewrite this part of it, sine x, sine y, minus cos x, cos y, plus sine x, sine y. And now here we have cos x and cos y. We have a positive and then a negative version of it, so those cancel. And then this will equal, if we just add these two up, since they're like terms, it'll be 2 sine x, sine y, and that is equal to the left side, sine x, sine y. So the left side and the right side equal, and we've proven the trigonometric identity. And now moving into our last problem, so problem number 6 here. So in this situation, again, I'm going to rewrite the equation, or I guess the identity, but I'm going to rewrite it while putting sine of x and cos of x in for tan. So this is 1 plus sine of x over cos of x, and this is 1 minus sine of x over cos of x. So in this problem, this one's a little bit more complicated, but I'm going to still deal with the left side first, and then do as many manipulations as I can, and then go to the right side. So here we have 1 plus sine 2x. Well, I know that sine 2x is really just 2 sine x cos x. And then I also know that cos of 2x, well, that's really just cos squared x minus sine squared x. I also know that this 1 right here can be written as sine squared x plus cos squared x, and then this will be plus 2 sine x cos x over, and here we have an a squared minus b squared. So again, we have a difference of squares. So this will be cos of x minus sine of x multiplied by cos of x plus sine of x. And I'm going to rewrite the numerator to make it a bit more clear, but what we have is sine squared x plus 2 sine x cos x plus cos squared x, and that's all over cos x minus sine x multiplied by cos x plus sine x. And again, I told you this one was a tricky one, but we're going to have to now use this and understand that this is really just a squared plus 2ab plus b squared. So this is our perfect square trinomial in the positive form. So here, this can be summarized as sine of x plus cos of x, and then I'll just rewrite it. It could be squared, but I'm going to rewrite it as sine of x plus cos of x over everything down here, cos of x minus sine of x, and then multiply cos of x plus sine of x. Now I think you can see that this numerator, this here and here, the numerator and denominators can cancel. Then we'll have sine of x plus cos of x over cos of x minus sine of x. So it's at this point where I'm going to start working with the right side of the equation. So that's 1 plus sine of x over cos of x, and then we have 1 minus sine of x over cos of x. And here, I'm going to kind of get a common denominator here. So we have a 1 plus this fraction on the numerator, so I'm going to get a common denominator, which will be cos of x. So this will be cos of x plus sine of x over cos of x. In the denominator, I'm going to do the same thing and get this common denominator between these two. So this will be cos of x minus sine of x over cos of x. And this looks pretty, like, I guess, messy and not very clear. So what I'm going to do is I'm going to write the top part of this expression like this. And then I'm just going to, this over sign right here really just represents division, right? So I'm going to write divided by, and then I'm going to put this over here, cos of x minus sine of x over cos of x. And when we're dividing by fractions, what we really do is we multiply by the reciprocal of that fraction. So this is actually times cos of x on top over cos of x minus sine of x on the bottom. And here, this is where the cos of x will cancel, and we will get this cos of x plus sine of x over cos of x minus sine of x. And that, of course, is equal to this left side here. We have cos of x in the numerator minus sine of x. So we've proven this trigonometric identity. So I find that a lot of students find trigonometric identities extremely difficult. I think that they're not very confident in where to start and where to end and kind of see these relationships. What my advice would be is just to kind of start and go with whatever pattern you see right away. There's multiple different ways to use these identities and prove them, so I would just go whatever one you see first. And again, I think it's really important to stress that you should really derive these formulas and understand where all of them come from, because whenever you just look at a formula sheet, if you don't see it right away, you're going to get kind of like paralysis by analysis and you're not going to start at all. So what you really should do is understand the relationships between them, so then your brain gets quick at understanding where these relationships lie and what actually can be converted to what. Thanks for taking the time to watch this video. If you like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content to help with math and physics tutorials, as well as how to improve the mindset and learning skills of the student. If you guys have a certain topic you want me to cover in the future, let me know in the comments down below. Thanks again, and I'll see you guys in the next video.